Hello everyone, before starting the lesson, try the warm-up. Is this relation linear, quadratic, or exponential? You may recall from a previous lesson how to tell if the function is linear, quadratic, or exponential based on the table of values. So pause the video and try to see if you can come up with an answer. So you might have tried to find the first differences, and you'll notice they're not all the same, not even close. So then you try the second differences, and they're not all the same either. So I can conclude this is not linear and it's not quadratic, so then I try to find the ratios between my first differences, and I see that they're not all the same either. So it's not exponential, I guess. If I had to pick between these three, I would have to pick exponential because the numbers are a lot closer than they are for the first differences or the second differences. So I'm going to say an exponential model fits this data the best. Better than linear, better than quadratic, even though it's not fitting the data perfectly because my ratios aren't all constant perfectly, but they're pretty close. This is going to be the best model. So this is an example of a real-world application. If you gather data in the real world, your mathematical model to describe the relationship between your variables is not going to fit perfectly with what you have observed. So we go with what fits the best. In this lesson, we're going to talk about applications of exponential functions. So we're going to use exponential functions to model and solve problems. I mentioned this in the warm-up, but with real-life samples, the numbers usually don't fit a mathematical model perfectly. We need a curve of best fit. Now in grade 9 and 10, you might have talked about a line of best fit when you make a scatter plot, but that only works for a linear model. If you have a quadratic or an exponential model, then you'll have a curve of best fit. So I want to show you how you can use software to find the curve of best fit for your model. Now you can try to follow along. We're going to try to make a graph with a curve of best fit for the data that I had in the warm-up. So go to desmos.com/calculator. If you've never used this before, it's a very easy to use graphing calculator. Once you're in there, you want to go to the plus sign and select table. Then you can start inputting your data. Use number of hours for the X variable and bacteria population as the Y variable. So you can pause the video and take a minute to create your table of values. So pause the video and try that on your own. Now I will go back to this Desmos graphing calculator in a second, but first, for a simplified model, which we're going to use today, we can use this function, y equals a times b to the x. I'm ignoring the c value for now, just to simplify our model. So remember when I said a plus c would be your y-intercept? Well, if we're ignoring that, then a would be your y-intercept or your initial value. B, the base of your power, will be your growth or decay rate. So keep this idea in your mind. We're going to create an equation in the format y equals a times b to the exponent x. So here's the example. We're going to write the equation of the exponential curve of best fit for the bacteria population growth in the warm-up. So we've already inputted our table of values. We've got the number of hours, and we've got the bacteria population. When you input the table of values, you will get those points plotted on the scatter plot. Now I've adjusted the scale on the x and y axes so that you can see it. Now to get the actual curve to go through your points, you're going to type this into the next line. It's not y equals a times b to the x. We don't use the equal sign, we use this. it's a tilde, or that little wavy symbol. So if you type that instead of an equal sign, that tells Desmos that you want it to come up with the equation. It's not that you're telling it the equation to graph. It's giving you the equation. Now, we don't just type y or x, we type y1 and x1. These are references to your table of values, so that it's making an equation to fit this table of values as opposed to a different table of values that you could also add below. So once you type this into Desmos, it spits out all this information down here. The r² value, I'm not going to get too much into that, but that's a statistical measure of how well this equation or this graph fits the data in this table. The closer it is to the number 1, the better the fit. So when it says 0.9998, that's really close to 1. So that means that this model, this blue curve, fits our data really well. It's a very good model to fit our bacterial population growth. Now down here, it says A equals, B equals. These are the values of A and B in the equation. Remember, the equation is written in the form y equals A times B to the x. So if I know what A is and I know what B is, then I can replace A and B with those numbers, and this is the equation that models my bacterial population growth. The y-axis shows me the population. The x-axis shows me the number of hours. So to calculate the population of my bacterial culture, I'm going to multiply 996.359 by this power, 1.14366 to the exponent x, which is the number of hours. So if I want to know what's the population growth after 10 hours, make this a 10. And then do the calculation, and you'll get the population that you would expect after 10 hours. So let's talk more about that equation. I've rewritten it at the top of the screen here so you can see it more clearly. What is the approximate growth rate according to the equation? Well, which number in the equation represents the growth rate? The base of the power tells me my growth rate. So 1.14366 is the growth rate. But what does that mean? It means the population is growing by about 14% each hour. 14% is 0.14, but this is 1.14. That means 114%. That means every hour we are 114% of what the population was in the previous hour. That means it's grown by 14%. So every hour the population is growing by 14%. If we look at what this is, 996.36, that would be the initial or starting population. So if we walk through the equation here, to calculate the population, we take our starting population, multiply it by 114% every hour. That corresponds to a 14% growth rate. Now in part C, use the equation to estimate the bacteria population after 10 hours of growth. Well, 10 hours of growth, that means x is 10. So I'll insert the 10 where the x is, and I'll do the calculation. 996.36 multiplied by this power. And if you do that in your calculator, you'll get approximately 3,814 bacteria as the population after 10 hours of growth. Notice I rounded my answer to a whole number. Because I'm talking about population, I'm talking about numbers of bacteria in this case. So we're talking about whole numbers of bacteria. Part D, predict when there would be 10,000 bacteria. So this time we know the population. We want to figure out when that will happen. So we're solving for x. We know the population. We don't know the time. Now there is a way to solve for the unknown exponent and get a precise answer. However, that's not part of this math course, so I'm not going to talk about it, but if you are interested in knowing a precise way of figuring out what the value of this exponent is, you can talk to me. For our purposes in this course, we're just going to use the method called guess and check. It's quite simple. We're going to guess a number to put in the x position. We're going to do the calculation with that value, and we're going to see what we get. If our answer is lower than 10,000, that means our x value is too low, and we try a higher one. If our answer is higher than 10,000, then we know x was too big, and we try a lower one. And we keep going back and forth, trying numbers here, do the calculations, see if your answer is too high or too low, and then make adjustments to your exponent. And you can get as precise as you want. I opted to round to the 1 decimal point. 17.2 hours approximately until you get 10,000 bacteria. 17 is too low, 18 is too high. It's somewhere in between 17 and 18, so then you just start adjusting the decimal place until you land on this. You can get more precise than my answer here if you want to try it, but this is called the method of guess and check. If this was a test question, I would expect you to write out the equation like I've shown here, and then tell me how you're finding out what your answer should be. So just write guess and check if that's what you're doing. You don't have to show me all of your guesses and what you did to check them. Just show me after that the final answer that you landed on. So if you're going to do guess and check, just write guess and check as part of that good communication for your solution. So once you have an equation to model your situation, in this case bacterial population growth, you can either solve for the y variable or solve for the x variable, depending on what it is you're looking for. Now, just recall, we're using a simplified version of the exponential function equation, a times b to the x. A represents your initial value, your y-intercept. B is your growth rate or your decay rate. So, let's change applications. In the year 2000, a town had a population of 4,000. Since then, the population has grown 2% each year. I'm going to use, instead of x and y, I'm going to use p for population and n for the number of years since the year 2000. Instead of y, I'm using p. Instead of x, I'm using n, but I need to know a and b values to make my equation. I want to be able to calculate the population in any year after the year 2000. So what numbers do I have to put in these positions? Well, a is the initial value. So what is my initial population? Well, it started with a population of 4,000 in the year 2000. So my initial value is 4,000. And what's my rate of growth or decay? Well, is it growing or decaying? It says the population has grown 2%. Now, 2% is 0.02, but if I put a 0.02 here, that's less than 1. That means I would actually be decaying. My population would be shrinking each year by 98%. That's not what I want. It's growing by 2% each year. So think of it like this. Each year, the population is 100% of what it was the previous year, plus another 2%. So overall, the population is 102% of what it was in the previous year. So if your population is growing by 2% each year, you're going to multiply by 1.02 each year. So this would be the equation to model the population growth per year, starting in the year 2000. Now let's do a similar thing with a different application. A brand new car was worth $50,000. Since then, the value has depreciated by 15% each year. Just so you know, depreciation means the value of the car is getting less and less each year. So we're going to use V to represent the value of the car in dollars, and N to represent the age of the vehicle, number of years. So to calculate the value of the vehicle a certain number of years after it was originally purchased, we need to figure out what the initial value was and the growth or decay rate. Well, the brand new car was $50,000. That's the original value. That's your starting point. That's your y-intercept. Since then, the value has depreciated by 15% each year. Well, 15% is 0.15. Do I put 0.15 here? No, that would mean the value of the car is 15% of what it was in the previous year, but it's depreciating by 15%. That means it's 15% smaller than what it was. If the value is decreasing by 15%, that means the value is 85% of what it was in the previous year. Let's back up. In the previous example, the population was growing by 2%, so it was 1 plus 2% to be 1.02 as the growth rate. Here we're depreciating by 15%, so we're going 1 minus 15%, so our value is 85% of what it was in the previous year. That's our decay rate. So that would be the equation to model the value of the car N years after it was made. Starts at $50,000, and every year it's 85% of what it was in the previous year. So just watch out with the wording. If you're growing by 2%, your growth rate is going to be 1.02. If you're decaying by 15%, your rate is 0.85. You're either adding to 1 or subtracting from 1 by the percent you're growing or decaying each year. Now in this example, it's talking about something called a half-life. I'll read the question, then I'll explain what a half-life is in case you don't know. A 200-gram sample of radioactive polonium has a half-life of 138 days. Let me explain what that means. You're starting with 200 grams of this polonium. Every 138 days, you're going to have half as much of the sample. So you start with 200 grams. After 138 days, you now have 100 grams. 138 days later, you have 50 grams. 138 days later, you have 25 grams. Every 138 days, you have half as much of your sample as you did before. So write an equation to model the mass of polonium that remains after D days. We're using M to represent the mass in grams, D to represent the number of days. I have blanks to fill in to make the equation. The equation is for calculating the mass. So remember, you need the initial value, the growth or decay rate, and then the exponent. Take some time to think about what you would put in each spot. You probably figured out this, no problem. We're starting with a 200-gram sample, so our initial value is 200. You might have had more trouble with what to put in here because it doesn't say it's decaying by such and such a percent. But remember I talked about half-life? Every 138 days, it's half as much. So you're decaying by 50%. Every 138 days, you have half as much as what you did before. Now, if you just put a D here, that won't be totally correct because the half-life isn't every day, it's every 138 days. So every day is 1/138th of the half-life. Once D is 138, this exponent is equal to 1. 138 divided by 138 is 1. That's 1 full half-life. That means you're going to have half as much. So you're going to have to make this little adjustment to your exponent when you're dealing with a half-life. The number of days divided by the half-life in days. Now this equation is set up to calculate for the mass. So in part B, how much polonium remains after 5 years? Just watch out, it's saying 5 years, not 5 days. Other than that, pause the video and see if you can answer part B and part C. For part B, we're figuring out how much polonium, that's the mass, we're calculating mass. After 5 years, years, I need to turn that into days because D is the number of days. 365 days per year for 5 years, that's 1,825 days. So I'll replace D with 1,825. I do that here. When you type this into your calculator, just be careful. You do 200 times 0.5 and then hit your exponent button. At this point, you want to put this fraction in brackets. So hit your exponent button, then press brackets, 1,825 divided by 138, close your bracket, then hit equals. You should get 0.02 grams. If you're not getting that, you should reach out for help before moving on. Part C, how long does it take for this sample to decay to 110 grams? That's the mass. How long does it take? We're figuring out what D is. So here's the equation. I'm trying to solve for D. I'm going to use guess and check. I end up with about 119 days. So it takes about 119 days for my 200 gram sample to decay to 110 grams. Here's a next example. A new car costs $24,000. Its value depreciates by 18% each year after it is purchased. Determine the value of the car after 30 months. Why don't you pause the video and see if you can do this? You'll have to make an equation first and then figure out the value after 30 months. So pause the video and try this on your own. Well, I started by making an equation. The initial value is $24,000. It depreciates by 18% each year. So if it depreciates by 18%, that's 1 minus 0.18, which is 0.82 as the decay rate. 30 months, but I need years because this depreciates by 18% each year. So we can't have a mismatch in the units for time. If this is a percent per year, then my time has to be in years as well. So 12 months per year, 30 months would be 2.5 years. Do the calculation. The value is going to be $14,613.22. We've looked at applications of exponential functions. So hopefully you can see how to make an equation based on a description. You need to know the initial value and the growth or decay rate. Once you have an equation, you can solve for a missing variable. If you're solving for the y variable, you can do that in your calculator by plugging in the x value for the exponent. But if you're solving for the exponent, you're going to have to do guess and check. Now it's time to practice. So there's practice questions listed here, and if you get into trouble or have questions, please reach out.